So good afternoon, everyone. We have Dr. Laura here with us, and she has joined us from Ireland. She's currently a research fellow at the Dublin Institute of Advanced Sciences, and she's also a lecturer at NASA GSFC. So today she'll be talking about the flaring sun and the solar flares and how they affect us.
Great, thanks very much. Hopefully you can all see my screen and hear me. So first of all, thank you for the invitation to give this talk. I'm happy to be here and to talk about my favorite star, which is the sun, and a little bit about my research. So what I'm going to do is kind of give an introduction to kind of the sun and the sun's atmosphere, the solar corona, and then talk about kind of what solar flares are. These are big kind of explosions on the atmosphere of the sun, why we care about them and how we study them. And also I'll kind of move on to some of the adverse effects it can have here on Earth, particularly on the Earth's ionosphere. And then I'll finish with kind of some future exciting opportunities that are becoming available now with the next solar cycle. So just to kind of give some background, this is a nice movie I have in the background here of the solar atmosphere of the sun, the solar corona, and we can see all these loop structures and lots of dynamics going on. And you can see there's intense brightening that occurs just around here. And following this brightening, you can see this whole kind of wiggling motion of all these loops. So these are magnetic loops in the atmosphere of the sun. So the solar atmosphere, the corona, is a compressive medium that's kind of filled with really, really hot plasma and really, really strong magnetic fields. And these are the magnetic field loops that we'll talk about. So just to begin, when we think of the sun, we might think it's very boring, right? If we look at it in white light or at the light that is sensitive to our own eyes, we'll see it looks like a disk, as you might expect in the sky. And if you look kind of closely during active periods of the sun, you can see sunspots. And this is an image that was taken by the NASA's Solar Dynamics Observatory, the HMI instrument, and it looks at the continuous. This is looking at white light observations from the sun. We can see these black structures here, and these are called sunspots. So I'm sure many of you have heard of sunspots in the past. If you actually had a telescope and you put a filter on it, you could actually look at them from Earth and see these sunspots when they're quite large. So what they are regions of really, really intense magnetic field. So the magnetic field is so strong that it's actually inhibiting convection. So it actually looks a bit cooler in white light. However, these are regions that are really, really strong magnetic field and are going to be really, really important for when I continue with this talk. And to give you kind of some scale, like this is the scale size of the Earth. So these sunspots are absolutely massive. They take over huge portions of the sun and kind of are larger than the size of Earth and other planets. Now, when you look at the sun like this, it doesn't look that exciting. There's not much going on. You see some sunspots. But what's interesting, and when we kind of get into the interesting dynamics, it's when we go into the atmosphere of the sun. And this is an image that we see with, again, Solar Dynamics Observatory, the Atmospheric Imaging Assembly, which is an instrument on SDO, and which takes images of the sun in extreme ultraviolet wavelengths. So we have to kind of go to wavelengths that are not sensitive to our eyes and to kind of hotter wavelengths, essentially. So we're seeing hotter plasma here. And we see that the sun is actually a lot more complex than we might think in what we see in white light. And some things to note here, this is looking at around 50,000 Kelvin. So actually, as you move away from the surface of the sun, weirdly, it actually gets hotter. And this is something that scientists still don't know the reason why yet. So the surface of the sun is around 6,000 Kelvin. This, as you move outwards in the sun into the chromosphere and the transition region and the corona, which is the atmosphere of the sun, it gets hotter up to millions of degrees. But these two images are taken at the same time. And we can see that these bright regions that we see, so this is really, this brightness here showing really, really hotter plasma compared to here. We can see the bright regions overlap with the kind of sunspots. So we're seeing in regions on the sun where the magnetic field is really, really strong, we're seeing these active regions, which are really, really bright, hot regions of the plasma of the sun, or the atmosphere of the sun. And if we kind of zoom in on this one active region and look in several different wavelengths, so we're looking again with the same instrument, but in different wavelengths. This is in 304 angstrom, this is in 131 angstrom, and this is in 171 angstrom. So this is, as you go in temperature, this is around 50,000 Kelvin, this is around 6 megakelvin, and this is kind of around 10 to the 7 Kelvin, so even hotter again. And what this image here is actually looking at a magnetogram image. So this is looking at the magnetic field strength from the sun. So we can see it's quite dipolar, right? So this is negative polarity and positive polarity. And this is thousands of Gauss. So it's really, really strong magnetic field. And if we kind of just play these little movies here, this will kind of show an evolution of this active region over time. We can see it's not stationary, there's an awful lot of dynamics going on. And we actually see this intense brightening. And we see this flashing here in this really, really bright, intense structure. It's so bright that it's saturating the detectors that are observing this active region. And what we observed just there is a solar flare. So what we're going to take away from that is that the sun is really complex when you go into the atmosphere of it. And there are these strong things called active regions and sunspots where we have this intense activity going on. And this has been known for a very long time. It's really in the space era, we've kind of been able to go to space and look at wavelengths in EUV to see the atmosphere of the sun. But people have been drawing sunspots and active regions with ground-based telescopes for hundreds of years. And you may have heard of the solar cycle. So this is the cycle that the sun goes through, where it goes through periods of having lots and lots of sunspots and periods where it's really, really low sunspots and the sun's not really doing anything. And if we plot the sunspot number as a function of time, this is only going back to kind of the 1970s, but this plot actually extends back to kind of the 1600s, from kind of astronomers looking at telescopes and drawing these daily, essentially. But we can see that the number of sunspots, or the number of active regions, essentially vary over an 11-year period. So essentially every 11 years, the sun goes through a period of minimum up to a maximum and then to a minimum again. So we see here in the last several years, we've been actually in a period of low solar activity and a solar minimum, as we would say. So just the takeaway here is that the solar cycle, was what we call it, has like an 11-year period. So every 11 years, it kind of goes through this maximum. And we can see over the last 10 years, it's actually the last solar cycle, which was solar cycle 24, was actually quite low. There wasn't an awful lot of activity compared to previous solar cycles. And what we can do is we can actually track these active regions as a function of time and plot them. And this was what this movie is showing, only looking at this last solar cycle. And we can see that these active regions move across the disk. So each kind of point here is an active region for a certain day. And we can see it kind of follows these two kind of structures, essentially, kind of two bands on the sun where we see active regions, which is interesting. And as we're kind of going as a function of time here, we can kind of plot out the number of active regions that actually occur in these two hemisphere bands. And then we can also plot the latitude. So this is plotting kind of where in latitude these active regions occur. And what you'll see here is it actually kind of follows what we call a butterfly diagram. So at the start of the solar cycle, active regions actually happen at kind of higher latitudes. And as the solar cycle evolves, it actually goes to kind of smaller latitudes. And the reason that we have this solar cycle and that we have these active regions in the first place is to do with the magnetic field of the sun. So unlike Earth's, where the magnetic field is just kind of a dipole structure, the sun's magnetic field is a lot more complex. And this is due to the fact that the sun is a big ball of gas and plasma. So it doesn't rotate like a solid body. So different portions of the sun essentially rotate at different speeds. And this will cause kind of this complex magnetic field structure because the magnetic field moves essentially faster at the kind of like equator compared to higher latitudes. And this is kind of this region that we have this magnetic field complexity, and essentially every 11 years the magnetic field of the sun flips around, and that's why we see this solar cycle. And so I just thought this was kind of a nice visualization to show kind of the evolution of the active regions as a function of time over the past several years. And as you can see, as we're kind of coming down this end of the solar cycle, kind of the number of active regions is starting to reduce. And as we'll see, kind of post 2017, there were kind of very few active regions essentially on the surface of the sun. So that's kind of all I wanted to say about active regions, but the focus of this talk is talking about solar flares. So what is a solar flare? So a solar flare is essentially a huge eruption in the atmosphere of the sun, which is caused by magnetic reconnection, and releases free magnetic energy that is stored in the atmosphere of the sun away. So a solar flare is essentially only a burst of radiation, so it's only light that we see. So I'll play this movie here. So this is the limb of the sun, or the edge of the sun, and this is again looking at EUV wavelengths, extreme ultraviolet wavelengths. We can see this evolution. You have a big eruption and you have this huge brightening in EUV. So this brightening is kind of several orders of magnitude larger than the quiet sun. And often associated with a solar flare is a coronal mass ejection, and this is an ejection of material away from the surface of the sun following a flare. And this is a movie here showing kind of several different instruments on top of each other. So this is AIA 171 angstrom, which is the same as this. And then we have two coronagraph images. So what this is, it puts a big kind of shield in front of the sun so that we can see white light kind of away from the sun to block out the kind of brightest light of the sun. And what we can see is we have this absolutely massive eruption of plasma and magnetic field away from the surface of the sun. And all these speckledy things here are actually energetic particles that are interacting with the detectors on board. So these things are extremely powerful. They're the largest explosions in our solar system. And of course, they can be detrimental if you have highly energetic particles escaping away from the sun. This can be really, really damaging. Luckily, on Earth, we have a magnetic field to kind of protect us, and we have a magnetosphere. However, if you're an astronaut in space, you have to be super careful about kind of these eruptions and coronal mass ejections and solar flares and energetic particles, because these can have, you know, fatal impacts to astronauts. And that's something that a lot of work has been going into recently, is to try to forecast these, especially with kind of the plans to go back to the moon and to go to Mars. Especially if you're going to Mars, you're going to be in space for, you know, 6 months, and you can't, essentially, you want to have ways to mitigate these effects. So together, when you have a solar flare and a coronal mass ejection, these are called a solar eruptive event. So when these two things occur together. But it's really the solar flare that I'll be talking about today, and that's this big burst of radiation. And the reason we really want to study these is because it is light. So when we see it, it's already happened. It takes 8 minutes from light to get to the sun to Earth. So once we've seen it, it's already happened. The effects are already occurring. But with a coronal mass ejection, it takes several days because it's moving a lot slower. It's not moving at the speed of light, obviously. So you have kind of some time to predict when it's going to arrive. Now, you know, we've known about these for sort of several years, and maybe we'll go back to the first ever recorded solar eruptive event, probably the most famous solar eruptive event, which was observed in 1859 by Carrington, who was a British astronomer who was doing daily sunspot drawings. So as I said, people have been looking at sunspots for several hundred years. And as Carrington was doing his daily observations of the sunspot drawings, what he saw was these two intense brightenings in the sunspot region. And he was so surprised that he ran down to get his assistant, and by the time he had come back, these intense brightenings actually had subsided. So this is the first observation somebody actually observed a solar flare, because before then you didn't have instruments in space to be observing these things, and there wasn't really an understanding of kind of how active the sun really was. We knew about these sunspots, but we didn't know about solar flares. What was interesting, there was also another British astronomer that also co-observed this at the same time, so it was incredibly lucky, but it was also incredibly large, and that's why we think that Carrington actually was able to observe it with his eyes. What was even more interesting is that 17 hours later, following Carrington observing this, there was a very large geomagnetic storm. So at this time, they had started to build magnetometers, which kind of records magnetic field on Earth. What they found is these huge variations in the magnetometer readings, so huge geomagnetic effects on Earth. And this was the first, you know, realization that the sun has significant effects on Earth. And they kind of were able to draw parallels to say, well, we saw this intense brightening on the sun, and then around 17 hours later, we saw this huge, intense geomagnetic storm. Maybe they are related. And what we recognize today is what Carrington saw was a solar flare, and obviously there was an eruption with it, but the eruption took a few days to actually get to Earth. But even more kind of interesting is that these were kind of observed across the whole. This effect was observed in kind of many aspects across the Earth. So this is a newspaper from the US in Louisville in 1859. And if we read it, it says, the auroral current from east to west was so regular that operators on the eastern lines could send messages to the city without the usual batteries being applied. The same extraordinary effect was apparent on the national telegraphic wires between Philadelphia and Pittsburgh. So what this means is that the geomagnetic effect of this solar flare and this eruption was so strong that it was driving currents in the Earth's ionosphere that was actually powering telegraph lines back at that time. There were also reports that telegraph wires were, you know, smoking and catching fire, and I think there were even auroral activities observed as far south as Cuba. So the auroral activities is essentially energetic particles from the sun interacting with the Earth's upper atmosphere. So this kind of today was, you know, we see this as a solar eruptive event. These things have been happening obviously before this Carrington event, but, you know, we didn't know of their effects. We didn't have a society so kind of dependent on the technological infrastructure. And this is why we kind of need to start thinking about the sun more and more now. Also, the sun is obviously a very interesting research topic to think about, but actually from a practical point of view, we need to understand space weather and how it is going to affect our technology. So back in this day, it was really only telegraph wires that were the things that were, the things that were going to be affected. But now, as we live kind of in a society so dependent on technology, from, our phones to our computers to satellites to power grids, all of these things are susceptible to kind of solar activity and space weather. So we need to kind of try to understand how space weather is going to affect these. And just to kind of give you some idea of solar eruptive events and some of the adverse impacts it has at Earth, I think we'll talk about a little bit about them now here. So the coronal mass ejection, so again, this is the ejection of plasma and material away from the surface of the sun. When these arrive, they arrive around 1 to 4 days after the eruption, so it takes that time to travel from the sun to Earth. And these can have really significant effects on kind of telecommunications, so they can interact with satellites, they can cause satellite drag. Power grids, so these kind of can cause huge geomagnetic storms in the Earth's kind of magnetosphere, and this can affect power grids, so essentially causing currents to run through power grids and blow transformers and things like that. Similarly, they can have currents flowing through pipelines, so oil pipelines, which can be a significant effect, and satellites. So even when I showed that movie that was looking at the coronal mass ejection, we saw those white little speckles. They were kind of energetic particles interacting with the detectors, but you can also have the kind of these energetic particles that would interact with the kind of electronic boards that would be on a satellite. And then these solar energetic particles that can actually occur during a solar flare, so these are accelerated both in the coronal mass ejection, but those accelerated in the flare can arrive up to 30 minutes from the flare itself. So this is really, really quick. And these are the things that are really detrimental to astronauts and spacecraft, and to any airlines that are flying kind of polar routes. So kind of things that are going close to kind of the northern pole or the southern pole, for example, because you have energetic particles that would be coming in to a kind of portion of the Earth's magnetic field. And then going back to solar flares, again, these are the kind of most prominent ones. This is when we see them, they're already happening. So we don't have any kind of leeway time to be able to say, what, there's a solar flare happening, turn down the power grids or something like that. And why solar flares are important is that it's ionizing radiation. So this is going to ionize the Earth's ionosphere, the ionized portion of the Earth's atmosphere. And this can cause radio communication blackouts. So high frequency radio communication can be blacked out for several hours. Similarly, it can affect GPS communication. So any kind of frequencies that are traveling from Earth up to a satellite, GPS depends on really precise measurements, and this can be affected by solar flare radiation. So these are kind of just a snapshot of some of the adverse effects of kind of space weather today. That wasn't maybe, it wasn't a thing maybe 200 years ago, because we didn't depend so much on these different types of, technology that we're so dependent on today. But today we've also moved a lot further than just kind of astronomers working in their home laboratories. How do we actually observe the sun today, and how do we understand all these different elements of space weather? So what we do today is we actually have a huge myriad of both space and ground-based observatories and different instruments that are observing the sun. And just to kind of give you some idea of what instruments we have on the ground and what we have on space, and we need to take into account the fact that the Earth's atmosphere blocks out lots of wavelengths. So for example, if you want to look at EUVs or in X-rays, you have to actually go into space away from the Earth's atmosphere to actually observe them. So if we look at the spectrum here, if we look at gamma rays and X-rays and UV and EUV, you have to be in space to be able to observe these, because you can't observe them from the ground. Visible light, of course, can get down, so we can have observatories that are looking at visible light. So there's several different ground-based observatories that are looking at this. You can kind of see some very kind of small part of the infrared that we can see from Earth, and then radio waves we can see from Earth, up to around kind of the low megahertz region before it gets blocked out by the ionosphere. So this is why we see kind of large radio telescopes that are ground-based, because you don't actually have to go to space to observe these. So yeah, our ground-based observatories are visible and microwave. But it's really into space we have to go to look at all these different wavelengths that we see. And all those nice movies I showed are from space-based satellites. And what I'm showing here is a snapshot of the NASA's Heliophysics System Observatory, or the HSO, which are all the different instruments that are currently in the near Earth environment that are looking at the sun and space weather. And so you can see there's a huge amount of them here. And some of these instruments are, of course, co-ran by different space agencies, such as ESA and JAXA and things like that. And I've circled the ones that are directly looking at the sun, and the ones that are kind of talk a little bit most about during these ones down here are kind of more looking at the magnetosphere and the effects of space weather on Earth, but these ones that are circled are looking directly at the sun. So kind of two ones to highlight is Solar Orbiter, which was launched in February of last year, just before the pandemic hit, and Solar Parker Pro Plus or Parker Solar Probe, which we call it now, was launched in 2018. So these are the new kids on the block. I'll talk a little bit about Solar Orbiter in a minute. And what type of data do we have now? We don't just have drawings of sunspots that we're observing. We have images of the sun, which I've shown. We also have time series of the sun, so we're seeing kind of data as a function of time. And we can have really, really high time resolution data up to kind of, microseconds. We also have spectra observations of the sun. So this is looking at kind of wavelength as a function. So emission is a function of wavelength, essentially. So essentially what we kind of have is it's really a data science a problem, essentially, in a way. As scientists looking at the sun, particularly observational scientists, we're glorified data scientists. We're using different types of diverse data to infer, scientific results. And there's lots of different elements to take into consideration here. You have calibration issues, you have kind of to take into account kind of the motion of the spacecraft, where it's looking at the sun, and different types of things like this, which is kind of interesting. And kind of moving into the modern era, we're living in a big data era, right? We're living in a world of kind of machine learning, and there's loads of data and lots of things going on. And this is actually a problem I say we have in solar observations today. And this is maybe different to kind of other aspects of astronomy where you mightn't have as much data, but because the sun is so close and we have this space weather aspect, we just have so much data from the sun. And because it's very easy to downlink as well if we have a satellite that's quite close by. So just to kind of give you some examples of how much data we do actually have, this is again looking at SDO, Solar Dynamics Observatory, and this is looking at one instrument, which is the Atmosphere Imaging Assembly, which takes 4K by 4K images of the sun in 9 different EUV wavelengths. So each one of these images is essentially a different wavelength or different passband that we're looking at the sun. And it takes an image every 2 seconds. So that's 4K by 4K image every 2 seconds. So that means that we have around 1.5 terabytes per day of data. And over the whole mission, since it was launched in 2010, there's 8.7 petabytes of compressed data. So that's compressed data of kind of, scientifically ready data. So this is actually becoming a challenge as you're a scientist working on your computer. How do you deal with 8.7 petabytes of data? And the problem even gets a little bit harder when you think about ground-based observations, because in space-based observations, you're somewhat limited to the fact that you have to downlink that data from the satellite. But on Earth, you don't have to do that. You're there, if you have a large enough computer beside your instrument, you can store all of that data. And just to give you an example, this is the low frequency array, or LOFAR. So there's several different LOFAR stations dotted all around Europe, which kind of form this giant telescope. But this is just the one that's located in Ireland. This is ILOFAR. And to give you kind of just an example, there's 3.2 gigabytes per second from this one station. So if you observe the sun for 6 hours, or if you observe, anything at night for several hours, that's 8.8 terabytes just for one observation. So as we're kind of moving forward, we need to start thinking about smart ways and smart tools to be able to analyze this data and to kind of make the most that we can out of this data to kind of infer these scientific results. And so I'll just take a little aside here just to kind of give you some idea of what this might look like in terms of how we actually study the sun and space weather. So I've kind of highlighted there's lots of different instruments and lots of different observatories looking at the sun. So each of these kind of different observatories that might be kind of provided by NASA or ESA or NOAA, or kind of instrument-specific satellites themselves, they kind of get the data from their satellite, they do some kind of pre-processing to it, and these are kind of like stored in some databases. They're provided to kind of level 1 scientific data, and then users can then query these through APIs in different ways like that. And then we have the kind of databases goes to science users and the space weather forecasters. And then when we have this data, how do we actually analyze it? And I think in the last, in the last 10 years, we've kind of the growth of Python as a software language has been really kind of you know, it's really kind of helped grow a lot of this interesting science, particularly making it accessible to both students, and you don't have to pay for expensive licenses. And there's also so many tools available and software tools for analyzing different types of data across lots of different industries, but a lot of it can be directly applicable to doing scientific analysis. So as a scientist looking at the sun and kind of lots of different other aspects of astronomy, we need software to be able to read data, to process data, and to analyze this data, whether that be to kind of read it in, to process it to kind of different scientific calibration levels, and then to analyze it. So we want to maybe fit the data, we want to plot the data, we want to do kind of interesting machine learning aspects to the data. And the Python scientific ecosystem has been really key in allowing this research to grow. I'm just kind of highlighting some of the kind of, if anybody's aware of Python, I'm sure that you've used it in your courses, or if you're going on to do grad school, you'll potentially use it too. All the different types of kind of packages that may be available, that are available, and that you may use, regardless if you're doing solar physics or astronomy and things like that. So particularly things like the machine learning packages. SunPy is a package that's kind of developed for solar physics research. And I think in ways we can kind of, you know, be better as scientists to make our science reproducible and to do the best we can with the data. You know, we're really moving to using these tools for analyzing large data sets. So kind of doing our work in cloud-based computing, such as like Amazon Web Services, and having version controlled and open source software. And that's really, really key for kind of new insights into science. You want to be able to produce reproducible science. So these are kind of some of the tools that scientists are starting to use now. Now, that's a nice aside to kind of talk about kind of the tools we use, but let's go back to the sun. Let's go back to talking about some solar flares. So how do we observe solar flares today? And how we do that is by looking at the GOES X-ray observations. So GOES is a series of satellites that was first launched in 1975, and they have an X-ray sensor on board. So this is looking at the X-ray emission from the sun. So it's looking, it doesn't image the sun, it's just taking a full disk integrated flux from the sun. And what we can see here is this is just on an active day in 2013. If we plot, these are the 2 wavelength bands in X-rays that we observe the sun in with GOES. And if we plot this as a function of time, we can see, you see all these different peaks that are occurring. And each of these individual peaks is essentially a solar flare. So this is during a very active time. And just to kind of give you some context of how large these actually are, this is, you know, this is on a log scale. So this is several orders of magnitude increase in the overall emission from the X-ray flux from the sun. So what that means is that even just in one small active region, you could have a flare large enough that the overall X-ray emission from the sun is going to increase by several orders of magnitude. And this is how we classify solar flares. We classify them based on their peak flux in this X-ray emission. So, for example, if it peaks above here, we can say it's an M-class flare. If it peaks above here, we say it's an X-class flare. So when I talk about kind of X-class flares, M-class flares, C-class flares, and this is what I mean here. So it goes A, B, C, M, and X. Don't ask me why it changes and doesn't go D and E, but I think this is medium and extreme. So just to kind of give you again some context of how often these solar flares occur, here is a plot looking at it as a function of time, and each individual dot is a flare. And the dot plotted on the y-axis here shows the peak flux in that X-ray observation. So here, you know, this was a very large X-class flare. And we can see as if we look at kind of the variation of these flares as a function of time, we can see that it follows some type of pattern. And if we overplot the sunspot cycle on top of that, we can actually see that it follows the solar cycle, which is something we kind of knew about before, but this is a nice kind of graphic to show it. It's interesting here, if we look at this kind of big line here, this is actually a region towards the end of the last solar cycle where there was a large active region with lots of sunspots, and it actually produced lots of flares, and actually 2 of the largest flares of the past solar cycle. Now, just again, focusing on solar cycle 24, and to kind of give you an idea of kind of the occurrence rates of these flares again, there are only 49 X-class flares. So X-class flares are these very large flares that we really are concerned about in terms of space weather. So there's only 49 of these over the past kind of 11 years. And then there's around 700 M-class flares and 7,000 C-class flares, and then more B and A-class flares. What we can do is we can take you know, each of these flares and plot kind of them as a frequency diagram. So this is looking at a histogram of the number of flares versus their peak flux. And what's interesting is we can see this nice parallel here. So this is showing that there's very few large flares and lots of small flares. And why this is interesting and why we kind of maybe want to study these parallel distributions of flares is something that might tell us about how the atmosphere of the sun is actually heated. I'll just note something here. It looks like there might be a turnover here for smaller flares, but that's actually to do with the fact that when the sun is so active, the base class level of emission from the sun is actually at a C class level. So when the sun is so active, we just can't see the smaller flares. But going back to why this is interesting, if we look at kind of this parallel distribution, so this is the number of flares by the energy essentially of the flare. This parallel indices, so this index here, if it's approximately 2, that tells us that there are lots and lots of small solar flares that are actually heating the solar atmosphere. So again, going back to that point that we don't know why the atmosphere of the sun is hotter than the surface of the sun. So if you think about it, like if you walk away from a fire, it should get colder. But on the sun, we find that when you walk away from the sun, it actually gets hotter. Something we still don't know about. So we're really trying to understand the frequency of these solar flares, the frequency distribution of these solar flares to understand essentially how that index might change. And just kind of to give some example, this was that was just only looking at the GOES X-ray observations of solar flares, but we can use different instruments and kind of observations to look at smaller and smaller flares. So this is kind of showing this going to flare energies which are much lower, so nanoflares and microflares, and different studies that have tried to kind of piece together what this flare frequency distribution might look like. And to give you kind of this is a really nice plot which shows like 2 super flares on other sun-like stars with the Kepler instrument. So we've seen other stars similar to the sun that have shown absolutely enormous solar flares or stellar flares. And the question is why did they occur, and can they happen on our own sun? So these 2 plots, these 2 points here are not on our own sun, but on other stars similar to our sun. And the question is, does it follow a parallel? Is there going to be a case essentially that maybe 1 every 1,000 years we're going to see a super flare on our own sun? And just to kind of give you, this spot here is kind of the largest solar flare we've seen in recent histories in X17, and it lies around here. So as scientists, we're really trying to understand this parallel distribution and try to fit different points on it, which is interesting. So just to kind of move on, some characteristics of solar flares. How long do they occur for? So solar flares, they can occur from minutes to hours, and it really depends on the solar flare and what wavelengths you're looking at. So this is an example looking at several different wavelengths from the sun during a solar flare. This is the GOES flux, which I showed previously. And this is looking at hard X-rays, so higher energy X-rays up to 50 keV. And this is looking at radio and microwave observations. So we can see during this flare, it occurred for around 20 minutes. Where do they occur? I think I've alluded to it a lot during this talk so far, is they occur kind of in active regions kind of associated with complex magnetic field. So when the magnetic field structure, this is the magnetogram here again, looking at positive and negative magnetic flux. When it's really complicated and the positive and negative magnetic flux is all intertwined, that's kind of the times you're going to have kind of the largest solar flares. And I've talked about, solar flares and eruptions or coronal mass ejections. And is there always an eruption with a solar flare? And the answer is no. However, when you have a large, say an X-class solar flare, it's almost 100% of those X-class solar flares are associated with an eruption. And then this is reduced for kind of the smaller flares. So I think the takeaway here is that not all flares need to have a CME associated with them, but the largest ones always do. So how do we understand flares today? What is the kind of standard flare model that we have of looking at solar flares? So I'll show here, this is a cartoon where you have magnetic field and it kind of reaches up. And what happens is that you have reconnection underneath, and this reconnection releases the magnetic free energy stored in the solar atmosphere, as I mentioned. And you essentially have an eruption that escapes away from the sun, and then you have this increased kind of heating and particle acceleration down towards the surface of the sun. So just play that quickly again. You see this rising, oppositely directed magnetic field lines reconnect, and you have this energy release. I think this is an actual movie of looking at EUV observations with AIA, and it almost, it very nicely matches that cartoon that I just showed there of kind of how we understand solar flares. So we can see, this eruption, and then you have this really intense brightening in EUV. So essentially the driver that we think we kind of expect to be is magnetic reconnection, which is this rapid release of magnetic free energy. And if we look at kind of a cartoon structure, we have this energy release, a lot of particles accelerated away and a lot of particles accelerated down. And in terms of kind of how this cartoon works, this is the corona, or the atmosphere of the sun. The chromosphere is also the atmosphere of the sun, but it's kind of lower down, a lot more dense. So in the standard flare model, what we have is this, as I said, this huge release of energy. This accelerates charged particles, both electrons and ions, to really, really high energies. So these energetic particles, accelerated particles, can escape both away from the sun and both be trapped within the magnetic loop. Those that escape away from the sun, so they're going to escape along open magnetic field lines away from the sun into interplanetary space, and they're going to cause type 2 or type 3 radio bursts that we see in megahertz frequencies. So these are the types of observations we'll observe with ground-based radio instruments and some space-based radio instruments too. However, it's the energetic particles that are trapped in the loop that are kind of maybe the most interesting from an energetic point of view. When you have energetic electrons that spiral along the magnetic field line, they're going to emit gyrosynchrotron radiation. And this gyrosynchrotron radiation we can observe as microwave observations. So we're looking at microwave observations from, say, 1 gigahertz up to around 30 gigahertz. We see brightenings caused by these energetic particles. Now, when these energetic particles interact with the dense region of the chromosphere, so you're going to have a denser region of plasma, they're going to lose their energy and emit non-thermal bremsstrahlung, which we see as hard X-rays. So X-rays kind of above 20 keV. So we're going to see these as kind of bright hard X-ray footpoints, as we call them. And then this kind of, the energetic particles losing their energy, they're going to heat up the region. And if you think of this structure in kind of a 3D loop structure, you're going to see brightenings along these two, what we call ribbons, which are kind of would emit brightly in EUV. Now, following this kind of release of energetic particles and how it interacts with the plasma, what you're going to have is at these footpoints, as I said, you're going to have emission of hard X-ray. But these energetic particles, as they lose their energy, they're going to heat the plasma to really, really high temperatures. And essentially what you're going to have is this hot plasma has nowhere to go. It's going to fill back up into the loop. And this is what we call chromospheric evaporation or ablation, where you have a pressure gradient and this hot plasma fills back up in the loop. And that's when we see this emission in soft X-ray and EUV. So if we think back to that movie that kind of showed that loop structure in EUV, that's essentially this really hot plasma that's coming up from the chromosphere that's heated by these energetic particles. So overall, what you have is essentially a physical mechanism that generates emission across the whole electromagnetic spectrum. So we see radiation from gamma rays all the way up to radio waves. And during this flare, you can have increased solar output by orders of magnitude. And I'm going to talk a little bit about why that's important. If you think about the sun being in the sky, and then suddenly you have a flare, it's going to get brighter in all these different wavelengths. So it's something that we need to think about when we're going back to space weather and how it's going to impact our ionosphere. And I'll just quickly give an idea. We have this standard flare model that I talked through. It's a standard model, but do our observations actually, follow the standard model? And in some cases, the answer is yes. This is looking at X-ray observations from the RESI instrument. So RESI, unfortunately, the end of its lifetime was in 2018, but it was launched in 2002, so it had, lots and lots of years of observations. And this is a nice observation looking at this grayscale here is looking at EUV. So these are these EUV ribbons. These in the blue circles here, that's looking at the hard X-ray. So we're looking at, really high energy X-rays, and we can see these footpoints. Then we can see the soft X-ray filling the loop. And if we look at the spectrum of this, so this is looking at the emission as a function of energy, we can see we have a nice thermal distribution looking at the hot plasma. And then you have a non-thermal distribution, which is looking at this hard X-ray non-thermal bremsstrahlung. So our standard flare model can maybe explain this case, and it can explain how here again, this is the soft X-ray emission. We can see the hard X-ray emission occurs during the impulsive phase when you have this acceleration of particles, first energy release, and then this heating and decay of soft X-ray occurs for a very, very long time. So in some cases, the standard flare model works very well. However, there's so many open questions we don't understand about solar flares. For example, we don't know what triggers them. We don't know, why does a solar flare just occur? Why is there all of a sudden magnetic reconnection and this release of energy? We don't have a good handle on that yet. we don't know how the charged particles are accelerated so efficiently. So we can understand how charged particles would be accelerated through this energy release, but how are they accelerated so efficiently? You have all the charged particles almost in that region are accelerated all at once. So how does that happen? And while we know that, this reconnection or this energy release happens high up in the corona, we still don't have a really good understanding of how it gets from the corona to the foot points. We're assuming it's electron beams that kind of propagate down the loop, but we don't understand the transport effects of those electron beams within the loop and within the plasma, and how does the energy actually get from one place to the other. In terms of continued energy release, sometimes we see after solar flare occurs, we see emission for a very, very long time, longer than the predicted kind of, radiative and conductive cooling times. So there is continued energy release that we don't see. So this is something we really don't understand. And why we want to understand these questions, we want to understand them from a fundamental physics point of view. It's a really interesting, plasma physics problem, astrophysical problem. However, we really want to understand these questions from a practical point of view because we want to understand the physics behind these solar flares. We want to understand that because we want to be able to predict them. We want to be able to predict, a really sustainable forecast of kind of like why they occur, how they occur, and particularly when are they going to occur. We want to build a forecast that will say, in 12 hours it's going to be a large solar flare. We have to be careful about, how our ionosphere is going to respond. We have to be careful about astronauts in space and so on and so on. And I think now what I'm going to talk about is just one aspect of solar flares and one aspect of how solar flares impact the Earth's ionosphere. So the Earth's ionosphere, for those of you who don't know, is kind of the portion of the Earth's atmosphere that's ionized. In terms of altitude, it kind of begins at around 60 kilometers in altitude and extends all the way up to 1,000 kilometers in altitude. And why it is so susceptible to solar flares in one way is that it is directly linked to solar output. The ionosphere is created by the sun, by radiation from the sun ionizing the atmosphere. So any changes essentially in the solar output is going to have direct impacts on the Earth's ionosphere. And in terms of kind of regions of the Earth's ionosphere, so there's different regions depending on altitude. So we have D, which is the lowest lying region. We have E and F, which is kind of much higher up. And if we look at the electron density as a function of altitude, here, this shows us maybe how susceptible the Earth's ionosphere is to the output of the sun. So what we have here is two kind of plots, one during solar minimum, so that's when the sunspot number is really low, and one during solar maximum, and this is when the sun is really active, there's lots of sunspots, lots of flares. And then we also have a day-night cycle, so obviously when it's nighttime, that portion of the ionosphere doesn't see the sun anymore, it's going to be reduced in its electron density. So yeah, nighttime you can see there's a lot lower electron density, and then in daytime it's a lot higher. And interesting, you can see these individual little bumps, and each of these individual bumps is how we define these different regions of the ionosphere. And the one I'm kind of mainly going to talk about is the D region. So another reason why we care about the ionosphere plays a huge governing role in all radio communications. So if you think of any kind of communication that has to go to a satellite, it has to travel through the ionosphere, which is an ionized plasma, which again, any radio signal traveling through it is going to be affected. The ionosphere also allows us to have high frequency radio communications. So high frequency radio communications operate essentially by, you send up a high frequency radio signal, it bounces along portions of the ionosphere, bounces off the Earth, bounces off the ionosphere. So kind of the ionosphere allows for high frequency radio communications. And if we look at the kind of critical frequency in which a radio wave will reflect, this depends on the electron density. So if you've ever done a plasma physics course, I'm sure you've seen this before. So this is the electron density. So the critical frequency at which a wave will reflect is essentially related to the square root of the electron density. So if you have a higher electron density, it's the higher frequencies are going to be reflected. So that's just something to take into consideration that I'll talk about in a moment. So if you think about it, when you have a huge solar flare, you have X-rays and EUV that increase by several orders of magnitude. And this is going to substantially increase the electron density and the entire day-side ionosphere. So it's going to increase this electron density by orders of magnitude. And what's particularly interesting, or maybe not interesting, but bad essentially from a telecommunications point of view, is that it's these X-rays and EUVs that penetrate down to the lowest lying regions of the Earth's ionosphere, so down to this kind of D and E regions. And what this does, as I've tried to highlight here with this cartoon, is that high frequency radio communications can actually be attenuated or in certain circumstances completely blocked out. So essentially the signal gets so low it gets attenuated and essentially completely absorbed. You can also have any radio waves that are traveling through the ionosphere to kind of to satellites in space can be affected. You can have scintillation events and stuff like that. And particularly you can have, yeah, as I said, GPS disruptions and blackouts, radio blackouts. And observationally, what does this look like? So these are 3 examples. This is going back to the Carrington event. This is the first observation of the solar eruptive event I talked about at the start of this talk. This is looking at the magnetometer data. So this is looking at magnetic fields on Earth. And we can see there's actually like what they call a crochet in the magnetic structure. So this is actually when the solar flare occurred, we see this huge dip in the magnetic field. So what is actually happening is that the currents, the flare was so large that it caused the currents in the kind of E region of the Earth's ionosphere to kind of change so much that we have changes in the magnetic field that we see in this crochet. And then this is the eruption that we see later on. We can also see solar flare effects in total electron content made by GPS data. So this is looking at the dayside ionosphere, and you can see kind of like high electron density regions where the sun is directly overhead during a solar flare. And then particularly, this is looking at the NOAA D region absorption model, and we can see that during a flare, it actually blocks out radio waves up to kind of 30 or 35 megahertz. So this is where we're having kind of high frequency radio absorption. And this is really, really important for anybody that's dependent on high frequency radio communications. And to give you kind of a strong case for when this actually was really bad, if we look at kind of in 2017, September 2017, there was the 2 largest flares of our solar cycle, which I talked about briefly before. And this significantly affected the D region ionosphere. And there was actually reports of radio frequency blackouts for several hours. Now, why this was particularly bad is that these actually occurred at the same time as the really bad Caribbean storms, both hurricanes Irma and Jose, if anybody remembers. So during this time, during these hurricanes, normal communications was disrupted. Telephone lines went down and things like that. So people were hugely dependent on high frequency radio communications, particularly emergency responders. So unfortunately, at this time, those emergency responders couldn't depend on high frequency radio communications because the sun completely, it caused the ionosphere to essentially block them all out, which was really bad. Now, particularly, this was a case where there was a French aviation plane that actually lost communications with the ground for over 90 minutes, caused by this intense flare. And this goes back to, again, when you see the flare, it's already happened. So we didn't have, ways to say, maybe you shouldn't fly that plane now because it's going to be a large solar flare. I think it was all okay in the end, but again, this shows that the plane was actually flying in a region that was significantly affected by the solar flare. Now, I'll briefly just talk about how we kind of probe and understand, solar flare effects on the Earth's ionosphere, and particularly on the D region, which is this lowest lying region of the Earth's ionosphere. So the D region, as I said, is the lowest lying region. It's formed during the day by Lyman alpha emission. So this is around 1.6 nanometers, and this acts on nitric oxide. So it ionizes nitric oxide. And just to kind of give you an idea of kind of the output of the sun, this is when there's no flare. The brightest line is actually Lyman alpha, for anybody that might be interested in that. However, when you have a flare, we have, as I said, X-rays and EUV kind of penetrate down to these regions, and they ionize nitrogen and oxygen, which are kind of the dominant constituents that are in the D region. However, in terms of trying to probe the D region and see how they are affected by solar flares, it's actually really, really challenging, and it's probably the most not understood region of the Earth's ionosphere. The D region is too high for balloons, so we can't send a really big balloon up that would kind of have detectors on it to observe the D region. And it's also too low for satellites. Its altitude is too low for us to put a satellite there to observe the D region. But one way we can actually do this is by observing the propagation of very low frequency radio waves that propagate in the waveguide between the Earth and the ionosphere of D region. So these VLF waves are around 3 to 30 kilohertz, and they essentially propagate as a waveguide, as I mentioned. So when you have, during the day, you have this waveguide is fairly stable. However, when you have a solar flare, the upper portion of the waveguide is going to be significantly affected. It's going to come down and it's going to have a different conductivity profile. And what this is going to cause is essentially changes in how this VLF wave propagates. So in terms of how do we kind of, what generates these VLF waves that we can receive and observe, it's essentially large Navy transmitters. So when I talk about large, we're talking about 1 megawatt, up to 1 megawatt transmission power of these very low frequency radio waves that are used to essentially talk to submarines in the sea. So yeah, again, there's these large transmitters. Here's just a plot of all the different transmitters that are located around the world. And we can kind of pick up signals from each of these transmitters and look at the amplitude and phase of the wave, and that will tell us about kind of this upper portion of the D region. And this is because the Earth doesn't change, so the VLF amplitude and phase is going to be dependent on just this upper region. So essentially what you can do is you can set up these very simple receivers. So this is just an example of one we have in Ireland. And a really simple box. This is the Stanford Sudden Ionospheric Detector box. They cost around $100 US. And we can observe these VLF signals, both the amplitude and phase. And the amplitude and phase essentially contains information about the D region electron density and collisional frequency. So in kind of a way, we can remote sense how the D region ionosphere is going to be impacted by solar flares. And to give you an example of this, here is a plot of what the VLF amplitude looks like. So in Ireland, we're picking up it from a transmitter in Maine in the US. So we're looking at the ionosphere over this region. And what we can see is, we'll just ignore this sunrise and sunset because there's a lot of complex physics that goes on. But just during the day, there's no solar flares. It's pretty stable. You see a slight diurnal effect of the sun rising overhead. However, when you have a solar flares or lots of solar flares, we can actually detect them in this VLF signal, which is really, really interesting. And one of the only ways we can actually probe the D region, this lowest lying region, and see how it is actually impacted by solar flares. And one way what we're actually doing is using the ionosphere as a giant X-ray detector, which is kind of cool. So if we had a way to kind of calibrate that, we can use it as a detector to understand solar flares. And how sensitive it is really interesting. So this is some work that I did actually during my PhD, which looked at solar to see if we can actually identify pulsations, or these things called quasi-periodic pulsations that occur in solar flare emission. And is the ionosphere, sensitive enough to detect these pulsations? And we found that it actually is. So this is a movie of a solar flare that occurred under the limb of the sun, and it was showing this kind of pulsating nature. And if we looked at the ionosphere, or this D region electron density, what we found is that the ionosphere was actually changing its electron density in sync with these solar flare pulsations. This was the first time this is actually seen, and shows us that how connected the sun and the Earth really are on these very short timescales. So the time delay between the ionosphere responding to this X-ray flux is only, it's a matter of minutes. It's like 1 to 2 minutes, really. And if we look at kind of the D region absorption map over this region, we can see it's essentially oscillating with these pulsating X-ray flares, which is interesting. So the stronger the blue color, the higher the electron density in the ionosphere, and kind of how more degraded a high frequency radio signal would be, essentially. So this is trying to give you a snapshot of how we kind of understand solar flares and how they really do impact us on Earth. And I hope that was kind of an interesting kind of introduction to it. I'm happy to take some questions, but just to give you kind of looking forward to the future. As I kind of pointed out, we've been in solar minimum for the past few years, and we are kind of, down in this solar minimum portion. However, the sun is starting to wake up again, which is really exciting. This is just a plot actually made of yesterday, which shows that there were lots and lots of flares in the past week, which is really, really interesting. We haven't had any X-class flares yet, but we don't really expect them yet. And if we look, this is a picture of the sun from yesterday in 171 angstrom, and we can see there's these active regions beginning to form again. So if we looked at the sun maybe this day last year, it was completely empty, right? It was just looked like this. So it's a really exciting time in solar physics. We know we're kind of ramping up. This is the predicted solar cycle, sunspot numbers for the next solar cycle. So we're on this rise phase now. So we're hoping that we're going to have lots of more observations in the future. And I think looking to the future, there are lots of new and exciting opportunities with both kind of existing space and ground-based instruments, and some that have been launched very recently and have been kind of deployed recently on Earth. And one such instrument is the European Space Agency's Solar Orbiter, which was launched in February of last year. What's interesting about Solar Orbiter is that it has lots of different types of instruments on board, both remote sensing. So what that means is it's either taking a picture of the sun or it's remote sensing something, and an in situ instrument where it has a probe and it's actually going to measure, what is the temperature at this point, which is really, really interesting. It's now taking observations. And furthermore, what's kind of unique about Solar Orbiter is that it's not just going to, sit at Earth and look at the sun. It's actually going to go very, very close to the sun. It's going to do several different flybys by different planets. It's also going to go out of the ecliptic plane and go quite north, and we're going to see kind of a different view of the sun, looking at kind of the polar regions of the sun, which is something that hasn't really been done before with the different instruments that are on board. So it's really, really exciting. There is some preliminary data from several different instruments that are on board Solar Orbiter, but it's really in November of this year is when the kind of science nominal mission begins. So there'll be kind of continuous data coming down, which is really, really exciting. And from a solar flare perspective, we have huge new opportunities to now study solar flares. So as I tried to kind of highlight is that solar flares are really a multi-wavelength phenomenon. So we see them across the whole electromagnetic spectrum from X-rays and gamma rays all the way up to radio waves. And what Solar Orbiter provides is to have all these different instruments that detect all these different wavelengths on board on the same instrument. Whereas before we've had to use different instruments, and some instruments mightn't have seen certain things and things like that. But for the first time, we're going to have, an instrument that's going to be able to look at the flare itself. It's going to be able to see it in EUV. It's going to be able to see it in X-rays. And it's also going to be able to detect these in situ, escaping electrons. So it'll be able to, for the first time, connect the energetic electrons that actually, accelerate towards the sun to those that escape into space, and to try to help us understand some of these outstanding questions we have in solar flare physics, which is really, really exciting. So this is kind of a snapshot again, looking at X-rays and EUI. So we have kind of like imaging observations, we have spectral observations, we have time series observations, and again, this is looking at radio observations as you kind of move away from the sun. So it's really, really exciting. So just to kind of conclude and summarize what I talked a bit about today, a solar eruptive event are kind of large explosions that occur in the atmosphere of the sun, and they consist both of a solar flare, which is just the radiation portion of a solar eruptive event, and a coronal mass ejection, which is the eruption of plasma magnetic field away from the sun. And both of these things have adverse space weather effects. I mainly focused on kind of the adverse space weather effects of solar flares, and that's kind of the topic of my research. And it's the kind of interesting topic in a sense because, as again, when we see a solar flare, it's already occurring. Solar flares are really a multi-wavelength phenomenon. So we see emission across the entire electromagnetic spectrum. And they occur kind of in active regions with complex magnetic field. And as we kind of approach the next solar cycle, we're going to see more and more solar flares. While we have kind of a good understanding of the standard picture of a solar flare, there are still many unknowns. And I kind of try to highlight them, such as the energy triggering release, how this energy is transported, and how essentially its energy is dissipated eventually. In terms of space weather effects of solar flares, they have a significant effect on the Earth's ionosphere, particularly the D region. And again, the D region, as I mentioned, is really, really hard to probe, but we can do this by using remote sensing VLF observations, or very low frequency radio observations. And some of the work that's been done in the past, actually the majority of the work that has been done in the past, is looking just at, one X-ray wavelength from the sun and comparing it to how the D region ionosphere responds. However, different flares can have different spectral properties. And what I mean by that is that some flares have a lot more harder X-rays than other flares. They might have a lot more EUV emission than other flares. So we really need to understand not just, the peak X-ray flux and compare that to the ionospheric response, but to look at lots of different aspects of a solar flare, such as its spectral properties, where it is located on the disk, whether it's associated with a coronal mass ejection, and whether kind of the ionosphere is in a state already before it occurs. So imagine you have a large solar flare, it impacts the ionosphere, and then 10 minutes later you have another solar flare. Is that going to be more geophysical? Is that going to affect the ionosphere more? than just one solar flare? And these are questions that are still unanswered and something we're hoping to be able to answer with the next solar cycle and next kind of set of observations that we have. And I think kind of moving forward, as I said again, there are lots of exciting opportunities ahead to provide new clues essentially into solar flares, into coronal mass ejections, into understanding the physics behind these and how they can affect us here on Earth. So I think I'll finish there and I'm happy to take some questions.
Thank you, Dr. Laura, for that. That was exciting. If anyone has any questions, put it in the chat box or in the Q&A section. Aryaka will take these to the third.
Hello, ma'am. So our first question is from Deep. He's asking, are there any indications on solar surface over various wavelengths about an incoming solar flare?
Sorry, can you repeat that?
Yeah, sure. Are there any indications on the solar surface over various wavelengths about an incoming solar flare?
Yeah, that's a great question. So what we usually see is before a solar flare, if we look at kind of the photospheric or the lowest lying regions of the atmosphere of the sun, if we look at the magnetic field structure or the white light emission, we can see it gets more and more complex and you can have flux emergence essentially before a large solar flare. So that's kind of some ways. Sometimes we see small little brightenings in EUV before a solar flare. And that kind of gives us some indication, but we don't necessarily know how large that solar flare is going to occur or when it's going to occur. And a lot of people have been doing things now as we have an awful lot of data for the past 2 solar cycles. People have been trying to use machine learning efforts to see, is there something that humans can't pick up, but there's just so much data that maybe there are some precursors there that we don't know about. So yeah, we're kind of use those kind of images of active regions to identify precursors essentially to solar flares.
Thank you, ma'am. Another question from Deep is, how accurate is the butterfly effect of moving sunspots in predicting solar flares?
Yeah, that's another great question. It's something, again, we don't really know about because the magnetic field of the sun is really complicated and we still don't fully understand the dynamo and how it is actually created. The sunspot diagram isn't really used in a way of predicting solar flares. That's kind of on a larger scale trend. Like these solar flares are quite transient. They occur, infrequently and quickly, where the global butterfly diagram kind of gives us that evolution. One thing it can help us with is to try to understand, activity cycles. So why was the last solar cycle more active than this one? And that's where we can kind of use the butterfly diagram to try to help piece that together. It really tells us more about kind of the evolution of the magnetic field over a solar cycle rather than the evolution of the magnetic field over kind of a short period of time is when we see a solar flare.
Thank you, ma'am. Moving ahead, Aranapte is asking why the magnitude of solar flare given in the graph is decreasing every 4-5 years.
Why the magnitude?
Magnitude of solar flares.
The magnitude of solar flares every 4 to 5 years. Did I show that plot? I don't every 4 to 5 years. I'm not entirely sure, to be honest, which plot could that have been. If you mean why the kind of the solar cycle decreases, that was more an 11-year period, not in a 4 to 5 period. So maybe Aaron can ask that question again, maybe clarify.
Aaron, please clarify your question in the chats again. Deep is asking a question, what effects do the solar flares bring about in equilibrium black body nature of the sun?
Another great question. And, again, it goes back to this kind of global scale, observation of the sun versus these transient events. And I actually don't know if anybody's really looked at that, to compare this, during, solar maximum versus solar minimum. So solar maximum when you have loads of solar flares and solar minimum. I don't know. I wouldn't imagine it would have a huge effect again because these things are transient. If you had a solar flare, a very large solar flare occurring, every day, and you had these massive solar flares, it might have an effect. But you'd imagine that the peak of the black body spectrum wouldn't change. It's not going to overall shift the black body spectrum.
Okay, thank you, ma'am. Next question from Deep is, Due to incident solar flares, does the ionosphere also radiate energy after some time? And if there are these emissions non-spherically symmetrical due to the varied electron density after the flares and thus bring about orbital changes to Earth?
That's actually a really great question. It's something I haven't really thought about. So we do know that like the ionosphere, of course, is going to emit, it's going to emit radiation if it's going to be recombining and things like that. But on a kind of, I don't think it would be large enough in any way to bring about any orbital changes of the Earth. And I guess it's just to do with the fact, I guess, that the Earth is rotating too. I don't think that's true. But it'd be interesting to see what kind of emission we do see from the ionosphere in terms of that radiation energy. I think it's quite low, but I know it does emit in like Lyman alpha and things like that you can see from space. Sorry, I don't have a better answer for that question, but I don't think it would change like orbital changes to the Earth.
Okay, moving on. Thank you, ma'am. Ayushman Jha is asking, do solar flares have an impact on the frequency of rotation of the sun on its axis? Do they make the motion irregular?
No, they don't actually. So they are quite large, but in terms of on the sun and the energy impact on the sun, the sun is just so large it doesn't have that much of an impact. You can have things like sunquakes and things like that, but it's not going to actually change any motions of the sun, essentially.
Okay, thank you, ma'am. Moving ahead, Bishwas Tiwari is asking, how do we calculate the strength of fields of solar flare?
How we calculate the strength of the magnetic field of solar flares?
Yeah.
Yeah. So what we can do is we can look at the magnetogram images. So these are looking at the magnetic field, the photosphere, the lowest lying region, or the foot points of that flare. And with those magnetogram images, that's actually made measurements due to Zeeman splitting of certain lines. So maybe you've done that before in your physics course. So that's one way we can kind of estimate the magnetic field evolution that occurs during a solar flare. When you go into the atmosphere of the sun, it's actually much more challenging to kind of measure the magnetic field in the corona. So all we're kind of depending on is kind of the ground photospheric magnetic field measurements, which we have. There's an instrument on board, Solar Dynamics Observatory, which takes images of the magnetic field of the surface of the sun, every 45 seconds or so. So we can kind of, during a flare, we can kind of get an estimate of how much magnetic energy is released during an event. But it's something, again, that there are an awful lot of errors on, and something that we're really trying to, move forward to try to understand a bit better. And I know one of the instruments, DKIST, which has been built in Hawaii, I think that will really help us to understand that a little bit better.
Thank you, ma'am. Aryan Apte has specified his question. Is there any trend in solar flare occurrences? And is there any way to protect ourselves if the flare passes the magnetic field of Earth?
Yeah, so in terms of it change, it's going to affect the magnetic field on Earth. The way a solar flare is, because it is just light, if it occurs on the disk of the sun, so if we can see it, it's going to impact our whole day side ionosphere or magnetosphere. In terms of a coronal mass ejection, which is this ejection of plasma and material, we can make predictions if that's going to hit Earth. Like, if it's moving away from, the edge of the sun, we're going to say, okay, well, that's probably not going to hit Earth because it's moving in the wrong direction. CMEs can also kind of have an effect of whatever angle they come out at. They can also follow, the Parker lines away from the sun and impact Earth. So there are a lot of kind of really good forecasting models that are developed that kind of give us an idea of what kind of portion of the magnetosphere is going to be impacted, and kind of the orientation of the magnetic field of a CME actually, the orientation, it will depend on how geophysical it is going to be to interact with our Earth's magnetic field. So was there a first part of that question that I missed, maybe? No?
It was covered.
Okay.
Aryan, you can ask again if you have any doubts more. Next question is from Pranshu Pandey. He's asking, is it possible that Earth's core could also perform solar flares?
No, and the reason is due to the fact that the Earth's core, and we have this nice dipole structure, but we're not going to have, the Earth isn't a big ball of plasma on its surface, and you don't have kind of this, due to the very strong magnetic field and very strong temperatures on the sun, is when you can have kind of this locked in component where the magnetic field and the plasma are locked together, and this kind of allows for reconnection. So we're not going to see reconnection and kind of buildup of energy that you would see in the sun on Earth. But it's kind of the same process, I guess, on how a magnetic field is generated, but we're not going to see a solar flare effect, essentially.
Okay, thank you, ma'am. Harit Purana is asking, to what extent is ISS and the astronauts affected by geomagnetic storms caused by solar flares, and what technologies are implemented in order to prevent the damage?
Yeah, that's a great question. So in really extreme cases, if you think of kind of like gamma rays emitted from the sun, the wavelength of gamma ray is actually, you know, shorter than your DNA, so it can actually get in and cause significant damage. Particularly also with kind of highly energetic particles, you can have large enough radiation doses that can be fatal. So, you know, one way to mitigate that and to make sure that an astronaut isn't affected by solar flares is to make sure that they're not out on a spacewalk where they have absolutely no protection. So if you're in the ISS and you're protected, I mean, you might still get some, but you might not get all. And they can have, I think they're talking about building, you know, for longer space missions, having kind of like a contained metal shielding room within their space station that they could go into if there was a large solar storm. And I think we also have to remember that the ISS isn't actually that, it's not, you know, it's not really far out into space. It's still kind of within the gravitational pull of Earth, so it still has some protection of the Earth's magnetic field. So I think they're really thinking of ways to, you know, this is why we want to have forecasts, because we want to say, if you have a scheduled, you know, spacewalk tomorrow, don't go because we're going to have a large solar flare and things like that. And that's kind of ways we can mitigate it. There was also a study that was done, this is before, so during the Apollo missions, I don't think it was really realized how dangerous solar flares and solar coronal mass ejections could be to astronauts. And they actually did a plot to show retrospectively kind of the different Apollo missions that went on and solar flares. And they were extremely lucky in the fact that they actually missed some extreme solar flare events. And they were saying that if they actually went at a particular time, they could have had detrimental effects. So it's really kind of now that we're really understanding the magnitude of the effects of these things on astronauts. And yeah, I think the ways we're doing it is forecasting to not go outside your spacecraft and building kind of shields within to be able to protect the astronauts.
Thank you, ma'am. Moving ahead, Shri Hari Mittal is asking, ma'am, you mentioned that D layer of ionosphere react to solar flare. You also showed a graph of response of D layer. Can you please clarify what is the time lag between solar flare and reaction by ionosphere?
Yeah, of course. So when we see a solar flare, so when I was comparing the X-ray observations with kind of the ionospheric response, the X-ray observations are almost made at Earth. They're made kind of like in geosynchronous orbit, so, you know, not too far away from Earth. So the time delay between getting from your X-ray detector to Earth is less than a second. But the time delay that we see is usually on the orders of a minute to 3 minutes. And what that is, we call that the sluggishness of the ionosphere, or the delayed response of the ionosphere. And it's due to the fact, particularly in the D region, that there are an awful lot of neutral components. So essentially there's ionization going on, but there's also an awful lot of recombination going on. So it's essentially a balance of the ionosphere responding to this X-rays. And what they find is that even though the X-rays finish peaking, there's still kind of this recombination and complex ionospheric chemistry going on, that the ionosphere peaks kind of a few minutes later. And it's this balance of ionization and recombination. I think higher up in the ionosphere, where there's kind of less neutral components, where you don't have as much recombination, it's the time delay is smaller, so it can be, you know, on the order of a few seconds.
Thank you, ma'am. A question from Ayush Mishra. He says, what effects would solar flare have on the planets with very thin atmosphere like Mercury or on moons?
Yeah, that's a great question as well. It can have bad effects. I mean, again, it's like that thing, you mean, if we didn't depend on technology and things like that, these wouldn't be as bad. But what really protects us here on Earth is actually the magnetic field as well as the atmosphere. So in terms of planets with a very thin atmosphere and you were standing on it, you would get, you know, a huge portion of radiation. You might get X-ray radiation, which is really bad. You can cause cancers, and you can have higher energy radiation, which is important. Another reason for you thinking about going to Mars, it doesn't have as strong as an atmosphere or a magnetic field. So, you know, when we're trying to think of, are we going to go live on Mars? You know, there's so many different challenges, but space weather is actually one of them, because you don't have this protection of our strong magnetic field or ionosphere. So you get like we do get some impacts from the sun. We get sunburn, but on certain other planets you get really, really bad sunburn and really, really bad radiation damage. So yeah, I think so. In essence, what would happen is that just the radiation would get lower down to the surface of the planet. A lot of work has been done now when people are looking for exoplanets, and they're looking for life on exoplanets. One way they're doing it is they're trying to look also at the host star, and if that star is really, really active, it can actually have an impact on how a planet is evolving and whether that planet will have enough time to actually develop an atmosphere without it just being blown away by the host star. So I think we're just particularly lucky here on Earth of the conditions that we have.
Thank you, ma'am. We are done with the questions.
Okay. Well, thanks very much. That was great.
Thank you.
Thank you, ma'am, for spending time with us and us answering the questions.
No problem. It was great, and enjoy the rest of your conference.
Thank you.
Bye-bye.
Right, so we'll be concluding here out of asking you. Thank you.